So we know what resonance is, but then most physical systems have some damping associated with it. We considered 3 physical problems. We considered the RLC circuit. The LC circuit is a nice resonance circuit, but the resistor adds damping. We considered mass on a spring. Mass on a spring with forcing can have a very strong resonance, but here we assume some friction in the problem, so that gives us damping. And we considered the pendulum, say a girl on a swing with her father pushing her. At low amplitude, it's the same problem. We showed that the dimensionless equation is the same equation at low amplitude, but that one also has frictional damping. So the equation, the differential equation we derived for those 3 problems is the same dimensionless differential equation, which I write here as x double dot plus alpha x dot plus x equals cosine beta t. A key feature of this equation is that alpha is positive, and alpha represents the damping being proportional to the velocity. So let's solve this equation, and then we'll look at the solution at resonance. Resonance here means that beta would be equal to 1. Okay, how do we solve this equation? We look at the homogeneous solution first. We try x equals e to the RT. Remember, we get the characteristic equation r squared plus alpha r plus 1 equals 0 for the homogeneous equation. Quadratic equation, so r plus or minus equals negative b, negative alpha plus or minus the square root of b squared, alpha squared, minus 4ac minus 4 divided by 2a divided by 2. Of course, there are 3 cases here, but they all share a common characteristic. The first case is alpha squared minus 4 is positive. Then we have minus alpha plus the square root of alpha squared minus 4, which is smaller than alpha. So minus alpha plus something smaller in magnitude than alpha will be negative. Minus alpha minus the square root will also be negative. So in the case where you have 2 distinct real roots, both of the roots are negative. In the case where you have complex conjugate roots, so alpha squared minus 4 is negative, so this becomes the square root of a negative number, so this is the imaginary part, right? So the real part is minus alpha over 2 is also negative. And then in the case of degenerate roots, you have r equals minus alpha over 2, which is negative. So in all cases here, the real part of r plus and minus is going to be negative. And what that means is you're going to have exponential functions which decay in time, decay to 0. So the homogeneous solution decays in time to 0. The limit as t goes to infinity of the homogeneous solution will be 0, decays to 0. We say that the homogeneous solution in this equation is just a transient. Eventually, it will become small, and you can neglect it. What does that mean in terms of the physics? Remember that the solution of this equation is the homogeneous solution plus the particular solution. The 2 free constants are multiplying the 2 homogeneous solutions. The 2 free constants are determined from the 2 initial conditions. The homogeneous solution will decay to 0, taking with it the 2 free constants. so that the final solution will be independent of the initial conditions, right? The initial conditions represented by the two free constants, say C1 and C2, decays to 0 with the homogeneous solution. That means that the solution to this type of damped equation is a slave to the forcing function. The solution goes to the particular solution. The daddy pushing the child on the swing. The child can start any way she wants. She can run and start moving. But however she starts, eventually her motion is going to be completely determined by the way her father pushes her. That's the particular solution. So let's find the particular solution. We need an ansatz. So let's try the particular solution. How should we do this? Well, we can convert first to a complex equation, right? So we should do it that way, other than doing cosines and sines. So let's go first to a complex equation. Let me put that up here. We can have the equation to solve then is going to be z double dot plus alpha z dot plus z. And then cosine beta t I'll take to be e to the I beta t. So we convert to a complex equation. And remember that x here is going to be the real part of z, right? Because the real part of e to the I beta t is cosine beta t, matches the cosine beta t. So to solve this equation, we're going to try xp equals some constant times matching the right-hand side, e to the I beta t. So we're going to try xp of t equals a times e to the I beta t. Okay, substitute in the second derivative, z double dot. So because we converted to a complex differential equation, we're actually looking for z here, not x. So we're looking for z. So we're substituting into our complex differential equation. The second derivative will bring down I beta squared, which is minus beta squared. So we have minus beta squared a. The e to the I beta t will cancel. Plus alpha z dot. Z dot will bring down an I beta. So we have a plus alpha I alpha beta a plus z. That will be plus a. And that will be equal to the right-hand side, which is 1. And I cancel the e to the I beta t. We combine terms. So this is 1 minus beta squared. 1 minus beta squared. And then plus I alpha beta times a equals 1. And we have here then a solution for a. So a is equal to 1 over 1 minus beta squared plus I alpha beta. Okay. We're looking for our particular solution, and we found a. We can put that together. But I think now I want to consider the resonance case. So for resonance, we're going to have beta equal to 1. If alpha was 0, that would be the resonance we previously considered. Now we're considering resonance when there's a damping term. Alpha is not 0. So we put beta equal to 1 here. And then what do we get for A? Then 1 minus beta squared becomes 0. Beta equals 1, so we have 1 over I alpha. So A equals 1 over I alpha. And then what do we find for the particular solution? So remember, the particular solution will be the long-time solution. So ZP is 1 over alpha e to the I beta t, and x is the real part of that. So we get the particular solution for x is going to be the real part of a times e to the I beta t, where beta is equal to 1. So it's the real part of 1 over I alpha times e to the I t. Okay? And that will be our resonance solution. E to the it is cosine t plus I sine t. We're dividing by I, so that will be I sine t. So we get sine t divided by alpha. Okay? That's the particular solution for resonance, damped resonance. And that means that this will be the long-time solution after the homogeneous term decays to 0. How do we interpret this? There's two points to make note of. The forcing term is cosine t when beta equals 1, cosine t. The response, the solution for x, is proportional to sine t. So that means the forcing is pi over 2 out of phase with the oscillator. You can imagine a father pushing the daughter on the swing. The maximum push occurs not when the daughter hits the maximum height. The maximum push occurs at the bottom of the swing when the daughter has 0 amplitude. So you can imagine pushing. You don't just push as hard as you can when the daughter gets to the top of the swing. You push slowly and then maximum at the bottom. That's the pi over 2 out of phase here. The second point is that when the damping becomes small, the amplitude becomes large. The amplitude is proportional to 1 over alpha. So the smaller the amount of friction, the lesser the friction, the larger the amplitude. Certainly you would expect that under damped resonance. So let me review. We're considering this dimensionless governing equation for the 3 application problems that we previously considered. The defining feature of this equation is that there are 2 dimensionless parameters, and furthermore, this alpha is greater than 0. The fact that alpha is greater than 0 means that there's damping. The homogeneous solution decays to 0. You're left with the particular solution. We can find the particular solution most easily by converting to a complex differential equation where x will be the real part of z. We make our ansatz here. We solve for a, and then we consider what is the solution at resonance, so beta equal to 1. And we get the particular solution is sine t over alpha. Pi over 2 out of phase with the force and with an amplitude that is inversely proportional to the damping coefficient. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.